Okay, so now we're actually going to start to talk about, now that we understand some basic language and now that we understand kind of uh, what needs to be set up for an experiment, now we're going to talk about like good experiments versus bad experiments. So a lot of the times it's easy to start thinking good designs after you know what a bad design is. So we'll start with how to experiment badly. So, experiments are the preferred method for examining the effect of one variable on another. By imposing the specific treatment of interest and controlling other influences, we can pin down cause and effect, which is a big idea. So, good designs are essential for effective experiments, just as they are for sampling. Okay, so we saw that, just because you were giving out a survey didn't always produce results that were reliable or meaningful. So, I think probably the better way to talk bad versus good is to actually go through a bad versus good um, example. Okay, so a high school regularly offers a review course to prepare students for the SAT. This year, budget cuts will allow the students to allow the school to offer only an online version of the course. So, suppose the group of students who take the online course earn an average increase of 45 points in their math scores from a pretest to the actual SAT. Can we conclude that the online course is effective? Okay, so this experiment has a very, very simple design, right? You got a group of subjects, those are the students. They were exposed to a treatment, that was the online course, and then the outcome was the increase in math scores that was observed, right? So a closer look, let's hypothetically start giving some hypothetical ideas that could happen here, right? So a closer look showed that, let's say, many of the students in the online review course, they were actually taking these advanced math classes at their school, right? Like AP Stats or IB Math, right? So maybe the students in the online course actually improved their math scores not because of the online course, but actually because of the courses that they were taking in school, right? So this would be an example of confounding, right? There was that other lurking variable there, the idea that most of these students were taking advanced math classes in school, and so that's a possibility that there was, that could have been where the increase of math SAT scores happened. Okay, so many lab experiments would use a design like the one in the online SAT course example. Okay, just a very simple design. So there's experimental units, they impose a treatment, and then they measure a response. Okay. In a lab environment, simple designs often do work well. Field experiments and experiments with animals or people deal with more varied conditions. So, outside the lab, badly designed experiments often yield meaningless or worthless results because of confounding or because of other lurking variables that are involved. Like the SAT class, was it the online course or was it their actual math courses they were taking in school? Okay, so um, let's talk now about how to possibly experiment well. So the randomized comparative experiment is what we'll constantly be referring to when we talk about a well-designed experiment. So, the remedy for confounding is to perform a comparative experiment. So, in which some units would receive one treatment, and then the similar units would receive another. So, most well designed experiments will compare two or more treatments. So, let's suppose in that SAT course example, right? So, one way to fix that confounding problem would be to create a comparative experiment in which some students are going to be taught the SAT course in a classroom, but then the others who were similar students would take the online course. So now you wouldn't see so much of an issue as to uh, what courses they were taking in school. Now you would see, is the one course better than the other? And it could be that they do have the same. They are taking advanced math, but because the groups are of similar students and they're both groups have the similar math courses in school, then you can actually see the effect of the online course versus the course taking in a classroom. So, comparison alone isn't going to be enough. If the treatments are given to groups that differ greatly, bias is going to result. So, for example, if we allow those students to select online courses or classroom courses, you may see more self motivated students. They may be more likely to sign up for an online course, but then again, they are more self motivated. Okay, so you will get a bias result from this. Okay, the solution to that problem would be random assignment. So, in an experiment, random assignment means that experimental units are assigned to treatments at random, that is, using some sort of chance process. Okay. Okay, so let's take a look at how we could have randomly assigned in that SAT class. So this year, the high school has enough budget money to compare the online course with the classroom course. Okay, so 50 students have agreed to participate in an experiment comparing the two instructional units. Let's describe how. You would randomly assign 25 students to each of the two methods, okay? So using 50 slips of paper, okay? That's known as the hat method. So this would be the simplest way, to write students' names on a piece of paper and then mix them in a hat and then draw one at a time until you have 25 slips. Then those 25 will take the online course. The remaining would take the classroom course. Okay, using technology, give numbers 1 through 50 in alphabetical order by last name. Then use your calculator's random integer generator and find your first 25 students, and then the last 25 would take the alternate treatment. Table D would be a similar idea to technology, only this time you would label them 0, 1 to 50 because you have 2 digits. Okay. I'm out of order in my slides. Okay. So now let's just talk a little bit about kind of the major principles of a good experimental design. So the basic principles for designing experiments are as follows. So comparison. So you are going to want to use a design that compares 2 or more treatments. So we talked about this idea because otherwise then you don't know if it's a confounding or lurking variable going on without a comparison. The other idea is that you always want to randomly design. So you're going to want to use chance to assign experimental units to treatments. Doing so helps create roughly equivalent groups of experimental units by balancing the effects of other variables among the treatment groups. Okay, so random assignment should distribute the students taking advanced math classes, right, in roughly an equal number to each group. So it should also balance out the number of students with lots of extracurricular activities and those with part-time jobs in the classroom and online courses. Okay, so any factors that can also be an issue there would be randomly distributed between the 2 treatments as long as they're randomly assigned. So random assignment would help ensure that the effects of other variables like math courses or let's say amount of available time to study if you do a lot of sports or you work a part-time job, that they're actually spread evenly among the 2 groups. Okay. The next thing that you're going to want to do is to control. So keep other variables that might affect the response the same for all groups. So although random assignment should create two groups of students that are roughly equivalent to begin with, we still have to ensure that the only consistent difference between the two groups during the experiment is the type of SAT prep that they're having, right? So you have to control for the effects of other variables by keeping them the same for both groups. So for example, we should give all students the same pretest and the same actual SAT test at the same times on the same days. So you're going to want to control the length, the timing, the content, and something else is the instructor, right? So you're going to want to control the instructor of the SAT prep classes, right? They should be the same. How do you know if the online course is better than the classroom course if there's two different teachers that are instructing both of them? It could be the teacher. So you always want to control for anything else that could be a lurking variable, right? So you always want to control what you can. If you can't control it, then you randomly assign it, okay? And then finally, you're always going to want to replicate. So use enough experimental units in each group so that any differences in the effects of the treatments can be distinguished from chance differences between the groups. So because the two groups are okay, so you would not necessarily trust an experiment with just one student in each group, okay? The results would depend too much on which group got lucky and received the stronger student. So if we assign many subjects to each group, however, the effects of chance will balance out, and there will be little difference in the average responses in the two groups unless the treatments themselves cause a difference. So this is the idea of replication, right? So you're going to use enough experimental units to distinguish a difference in the effects of the treatment from the chance variation due to the random assignment. Okay. Okay. So let's take a look at this example, which will kind of demonstrate those four basic principles. And I always like to think of it in my head like, first you know that you're gonna want to have at least two treatments, right? The second is I actually would go in reverse order from 2 to 3. The second thing I'm going to want to do is make sure I can control whatever I can. Whatever I can control is why I randomly assign 2 treatments. And then finally, you're going to want replication, replication, right? Because you can't just make an assumption based off of just one experimental unit in each group, or in each treatment, I should say. Okay, so let's take a quick look at this example and then move on. So does regularly taking aspirin help protect people against heart attacks? So the Physician's Health Study was a medical experiment that helped answer this question. In fact, the Physician's Health Study looked at the effects of 2 drugs, aspirin and beta-carotene. Researchers wondered whether beta-carotene would help prevent some forms of cancer. The subjects in this experiment were 21,996 male physicians. There were 2 explanatory variables, each having 2 levels. So aspirin, yes or no, and beta-carotene, yes or no. Combinations of the levels of these factors form the 4 treatments that are shown in the figure to the bottom right. 1/4 of the subjects were assigned at random to each of these treatments. On odd number days, the subjects took either a tablet that contained aspirin or a dummy pill that looked like and tasted like the aspirin, but had no active ingredient. This is going to be called a placebo, but we'll get more into that later in our videos. On even days, even numbered days, they took either a capsule containing beta carotene or a placebo. There were several response variables. The study looked for heart attacks, several kinds of cancers, and other medical outcomes. After several years, 239 of the placebo group, but only 139 of the aspirin group actually had suffered heart attacks. This difference is large enough to give good evidence that taking aspirin does reduce heart attacks. It did not appear, however, that beta carotene had any effect on preventing cancer. All right, so now we'll explain how each of the 4 principles of the experimental design was used in the physician's health study. Okay, so comparison. Researchers used a design that compared both active treatments, so both the beta carotene and the aspirin, to a placebo, a dummy pill. Then they randomly assigned, okay? That was used to determine which subject received each of the 4 treatment combinations. This helped ensure that the treatment groups were roughly equivalent to begin with. So that was that chart that was here. So these are the 4 different treatments. They were randomly assigned to them. The control. The experiment used subjects of the same gender and occupation. So they kind of controlled the idea that could it have been men versus women who have more heart attacks or susceptible to different cancers. Also occupation. So they do say that some occupations have certain stress levels that can affect, your heart as well as cancer, okay, and other things that are involved in occupations. So all subjects followed the same schedule also, so it wasn't like they were taking it in the morning or in the afternoon or after this, or they were all taking it at the same time. Okay, and then finally the replication. Okay, there were over 5,000 subjects that were in each treatment group, so definitely did that part. Okay, so that's the end of this video.